Welcome back to part 3 on our video for U substitution. In the previous two videos, we've covered examples of how to do U substitution when it comes to indefinite integrals. And in this video, we're going to explore what it looks like when we use U substitution in the context of definite integrals. So, there are two methods for evaluating a definite integral with U substitution. Method 1 is to evaluate the indefinite integral as we learned above, then use the fundamental theorem of calculus using the original limits of integration. So let's see how that plays out. Our next example says evaluate the definite integral using the previously described method 1. We want to evaluate the definite integral from 0 to 1 of x times e to the power of negative x squared dx. So my choice of u in this scenario, I want to make u equal to negative x squared. And when I take the derivative of that, we end up getting du dx is equal to negative 2x. And then from here, if I solve for du, I get du equals negative 2x dx. So what we're going to do now is I'm going to go ahead and rewrite my original integral. And this is equal to, now I want to emphasize that this is not a standard notation, but it is the notation that I end up using. So because we've now converted or are going to convert our definite integral so that we are looking at the variable and we're integrating with respect to u, my limit of integration, or my lower limit of integration, is supposed to be some u value, but I don't know what it is. Same thing for my upper limit of integration. I don't know what that is either. So for both my upper and lower limit, I'm going to write u equals question mark. And again, this is not really a standard notation, but we'll see what happens when this plays out. So coming back here, I know that du is equal to negative 2 times x times dx, and that doesn't appear in my integrand, so I'm going to go ahead and divide both sides by negative 2, and if I do that, we get negative 1/2 du is equal to x times dx, and that is appearing in my original integrand, so I have x there and dx there, so I know that x times dx is equivalent to negative 1/2 times du. So coming back, I'm going to write e, and then negative x squared we're going to replace with u, and then x dx gets replaced with negative 1/2 du. And I can factor out the negative 1/2 since that's a constant. And the nice thing is the antiderivative of e to the u is e to the u. So this is going to equal negative 1/2 e to the u, and this is being evaluated from u equals question mark to u equals question mark. Now, because I don't know what these limits of integration are in terms of u, what I can do now is I can get everything back in terms of x. So this is equal to negative 1/2 e, and then u I'm going to replace with negative x squared, and now we're evaluating this with our original limits of integration. So it's going to be from x equals 0 to x equals 1, and negative 1/2 is a constant. I can factor that out, and now I'm evaluating e to the negative x squared, starting off by plugging in x equals 1, and then minusing or subtracting e to the power of negative 0 squared, like that. From here, we get equals negative 1/2 times 1 squared is 1, and then times negative 1, so that's going to be e to the negative 1, or the same thing as 1 over e, and then minus e to the 0 power is going to be 1, so this ends up being our final answer. Now, something else I want to emphasize is I mentioned u equals question mark is not a standard notation. And so an alternative notation that I have seen more folks write is, instead of writing u equals question mark, maybe for their lower limit of integration, they'd put u sub 1 and then u sub 2 for their upper limit of integration. Either of these are fine if you're in my class. I'm okay with either of these notations, but the u1 and u2 are probably a little bit more common notations. So method 2 is to change the limits of integration when the variable is changed. In other words, we'll solve for new limits of integration in the u variable. So the substitution rule for definite integrals says if g prime is continuous on the closed interval from a to b and f is continuous on the range of u equals g of x, then the definite integral from a to b of f of g of x times g prime of x dx is equal to the definite integral from g of a to g of b of f of u du. So example 6 says, evaluate the definite integral using the previously described method 2. And notice that this is the same definite integral that we saw in the previous example. So once again, I'm going to let u equal negative x squared. I'm going to take the derivative of both sides and get du dx is equal to negative 2x. Then I'm going to get du, which equals negative 2x dx. And then from here, I want to divide both sides by negative 2. So I'm at this stage, and my original limits of integration were 0 to 1. So I'm just copying down my original definite integral. Now, when I'm rewriting this and I am changing it so that my integral is in terms of u, I'm going to solve for new limits of integration. And the way that I'm going to do that is I know that this relationship exists here. So my original lower limit of integration was x equals 0. And if I plug that into the pink boxed equation, I would get u equals negative 0 quantity squared. And if I simplified that, that would just be u equals 0. So that is my new lower limit of integration, even though it's the same numerical value. That's how we arrive there. And then my original upper limit of integration was x equals 1. So if I plug in u equals negative and then 1 quantity squared, 1 squared is 1 times negative 1 gives me negative 1. And so this is going to equal negative 1. So my new upper limit of integration is negative 1. And then, just like we did previously, I'm going to have e to the u, and then x dx is getting replaced with negative 1/2 du. So I'm going to go ahead and factor out negative 1/2 now. Okay, and so negative 1/2 is the constant, and if I take the antiderivative of e to the u, that gives me e to the u. And now we are evaluating this with u equals negative 1 and u equals 0. So I'm going to go ahead and keep negative 1/2 factored out, and I'm going to go ahead and plug in negative 1, and then minus e to the 0. So I have negative 1/2. E to the negative 1 is the same thing as 1 over e, and then e to the 0 power is the same thing as 1. So notice that this is my answer here, and then this is my answer here, and we end up getting the same exact answer. So really, this is up to personal preference in terms of which method you want to use. In some cases, one might be a little bit more advantageous to use than the other, but again, either way, you should be able to get the same answer regardless of which method you use. And again, it's personal preference on which one you would like to use moving forward. In the next example, we want to evaluate the following definite integrals. So part A, we have the definite integral from 3 to 5 of 4t all over 2 minus 8t squared dt. So I want to use u substitution. I'm going to set u equal to the thing that when I take the derivative of it, its derivative appears somewhere in my integral. So du dt is equal to, I'm going to use the power rule, and negative 8 times 2 is negative 16, and then I am decreasing my power by 1. And notice that if I solve for du, I get negative 16t times dt, and that's almost in my original integral. I have 4t times dt, but not negative 16. So what I could do is I could divide both sides by negative 4, and that would give me negative 1/4 du is equal to 4t dt. So that's one way I could go about doing that. And so now 4t times dt, that expression would get replaced with negative 1/4 du. So my original integral is equal to, and remember, you can solve for new limits of integration, or you can, at the end, go back to the original limits of integration. And if I want to use the original limits of integration, you can either say u equals question mark, or you can have your lower limit, the notation be u1 and u2. So maybe I'll do that for now, but typically I use the u equals question mark notation. So 4t times dt, I'm replacing that with negative 1/4 du, and then in the denominator, I have 2 minus 8t squared, and that's just getting replaced with u. And negative 1/4 as a constant, I can take that outside of my integral. And I have 1 over u du, and the antiderivative of that is going to be the natural log of the absolute value of u, and this is being evaluated from u1 to u2. And now at this stage, I can plug in my original limits of integration, and I'm going to substitute u to be 2 minus 8t squared again. So I have equals negative 1/4 times the natural log of 2 minus 8t squared. Don't forget the absolute value bars. And I am evaluating this thing from t equals 3 to t equals 5. So this is now equal to, I'm going to keep the negative 1/4 factored out, and I'm going to have the natural log of the absolute value of 2 minus 8 times 5 squared is 25, and then minus the natural log of the absolute value of 2 minus 8 times 9. And then I'm going to close my bracket there. That's equal to negative 1/4 times the natural log. This is an example where it illustrates why it's really important that we make sure to include the absolute value bars, because 8 times 25 is 200, so I would end up getting 2 minus 200 here, and that's going to be a negative number, and we can't evaluate the natural log if we plug in a negative number. Negative numbers are not in the domain of the natural log function. So that's why it's important here to make sure to include the absolute value bars. And 8 times 9 is 72. So we get 2 minus 72 here. And so we get negative 1/4 times the natural log of 198. At this point, I can drop the absolute value bars because negative 198, if I take the absolute value of that, gives me positive 198. And then minus the natural log of the absolute value of 2 minus 72 ends up simplifying to 70. And so we can leave our final answer like this. And that concludes part A. All right, so here we have part B, and we want to take the definite integral from 0 to pi over 8 of sine of 2x to the 5th power times cosine of 2x dx. And previously I've said that if you're integrating and you need to use substitution that involves trigonometric functions, it's always worthy or it's worth your time to try and make your u value the inside of your trigonometric function. This is an example where that's not going to work for us, because if I let u equal 2x, then du is going to equal 2 times dx. And what's going to happen is I'm going to rewrite my definite integral. And so we're going to get u1 to u2 of sine to the 5th power of u times cosine of u, and then dx, if I solve for dx, I get 1/2 du. And from here, I don't know off the top of my head, or that's not an integral that's in our table of commonly known integrals. And so if I decided to go this route, I could solve this, but I would need to use another substitution. So let's go back and see if we can't solve this another way. Instead, what I want to do is I'm going to start off by making u equal to sine of 2x. And here, the reason that I'm doing that is because when I take the derivative of that, du dx ends up equaling, the derivative of sine is cosine. I have 2x, and then I need to use chain rule. So I would take the derivative of the inside, which is 2, and we end up getting that du is equal to 2 times cosine of 2x dx. And notice that if I divide both sides by 2, cosine of 2x times dx does show up in my original integral. So I'm going to be able to replace that with 1/2 du. So let's go ahead and take our original definite integral, and maybe to mix things up and to keep it spicy, I'm going to solve for new limits of integration, since I didn't do that in the last example. So I know that u is equal to 2x, and if our original lower limit of integration is x equals 0, then if I plug that into my equation, I get u is equal to sine of 2 times 0, which is equal to sine of 0, which is equal to 0. So my new lower limit of integration is going to be 0. And then let's see what our new upper limit of integration is going to be. So I'm going to take x equals pi over 8. I'm going to plug that into the pink boxed equation. So I have u equals sine of 2 times pi over 8. That gives me sine of pi over 4. And sine of pi over 4 we know to be the square root of 2 over 2. So that is my new upper limit of integration. And now we want to go ahead and use the u substitution that we're doing. So sine to the 5th power, or sine of 2x to the 5th power rather, that's getting replaced with u to the 5th power. And then cosine of 2x times dx is getting replaced with 1/2 du. So moving forward, I can factor out 1/2. I'm going to keep my new limits of integration now. And I have u to the 5th power times du. Now the antiderivative of u to the 5th power, I'm going to raise the power by 1 and divide by that new power. And I can now from here just say that my lower limit is u equals 0 and my upper limit is u equals the square root of 2 over 2. So here I don't have to change back to be in terms of x. So I'm going to factor out 1/2 times 1/6 is 1/12. And then I am now evaluating u to the 6th power with our limits of integration. So I would have the square root of 2 over 2 to the 6th power minus zero to the 6th power. So this is equal to 1/12 times, if I raise the square root of 2 over 2 to the 6th power, my numerator is going to be 8, and then 2 to the 6th power in the denominator, that ends up being 64. And if we multiply that and reduce, we end up getting our final answer to be 1 over 96. And that's our final answer for part B.